Alrighty, we've got some more folks trickling in. Awesome. So super excited for this talk. Light field AR is an exciting space, and I think we're all just super jazzed to hear about ways that your team can kind of mitigate some of the roadblocks and hear some of your insights. So excited for that. But this is Tomas. He's the CEO and founder of Surreal. As you already know, you're here and you're excited to hear him speak. Just a little background. He's got an amazing background in augmented reality, of course. He's turned an entrepreneur after 15 years of research at CERN and EPFL. I'm sure we have many questions that we have to ask. I know I do around that. But just, Thomas, show us all your amazing stuff. Can't wait to see it. Please, take it over.
Thanks a lot, Ashley. So, hi, everyone. I'm pleased to introduce you to Surreal, which tells what we do. We are a Swiss startup. Currently 20 people, mostly veterans from Intel Wound and the advanced photonics team of Magic Leap from Lausanne, which we inherited. And together we gathered the force to bring the natural display to the augmented reality. Why? Because it's not here, and because augmented reality has the potential to become our everyday tool in everything, from cooking to neurosurgery, and the main communication platform of the future. And I guess that most of us already agree on that it is inevitable, but also that there is still a lot of work to do before it is here. And we solve one of the problems, and very important problems. But before I dive in, I would like to rephrase the reasoning why we think that AR will be even bigger than we can normally imagine. We always fail to predict what new technologies bring, but the logic behind is very strong. So try to think with me. What makes us people is the ability to communicate. Without it, we would be quite unremarkable creatures. Just imagine that no one ever told you anything. And today we reach the point that we can access our gigantic shared mind, the internet, or practically anyone in the world within a second from our pocket. That's massive, that's amazing. But here's the downside. The digital worlds, or to put it this way, we already spend majority of our waking time by looking at the digital information. And we use for it the most busy input which we have. Our eyes provide us with over 85% of all the information we receive from outside. So if you sum it up, we already spend more time in the digital world than in the reality. And here is the downside. The digital world is quite separated from the real one on the flat screens. And that's why augmented reality can make it much better. I actually forgot to switch the slides. So the AR, by blending the digital information into the reality, makes that the data become just seamless, hands-free, personalized, and contextual add-on on the reality. That's much more natural way of receiving information. It will liberate us from the flat screens and bring us back to life. It will upskill us. It will make us more creative and productive. And once powered by AI, it will become literally the prosthetics of our mind. And today, most of the AR ecosystem massively evolves towards this vision. But the display technology still needs revolution. And here is why. What we would like to experience in AR is something like this: entirely realistically looking digital objects in our own hands. But what we get instead today is still kind of a blurred potato. And this is not a problem of yet too low resolution displays or yet too bad optics. This is a problem of fundamentally wrong way of displaying 3D imagery. Because practically all displays we have, at least in commercial devices, are just flat. And even all the 3D headsets just magnify flat image and place it into a fixed focal distance in front of us. So two such images create the illusion of depth due to our stereoscopic vision, but each one eye sees a flat image. And this is a massive problem for AR because our eyes work like camera lenses and need to focus at the correct distance. It cannot focus at two different distances at the same time, like this. And you can experience how strong is the effect on your own eyes if you do a small test together with me. So if you close one eye and look at this display over your hand, like this, you can try to touch the text with your finger. With one eye, that's important. And you will notice that you cannot, right? You either focus at the hand and then you see like literally nothing behind, or you focus on the text. So you can't see both next to each other. So basically, this is what you should see when you focus on your hand. And that's why we can find images like this in the documentation, for example, of Microsoft HoloLens, telling the content developers to place the digital objects far. This prevents the problem, but it is not a solution. And of course, we can display the images close, but then the effective resolution drops massively, 10 times, 20 times, when we focus at the hands. Or if we don't see any real reference, like our own hands, the eyes have tendency to autofocus at the display. But on the account of terribly wrong behavior of our eyes, which leads to an eye strain, which you probably know, and nausea, and even if you don't feel it, typically within 20 minutes, it's not healthy for your vision. It's like wearing wrong glasses. So, and the closer we display the digital objects, the bigger is the conflict. So this makes today's display technologies with the flat screens the no man's land within the arm's reach. Within the arm's reach, the space is the no man's land for the display technologies today. And it has its own name, divergence accommodation conflict, and popular media are starting to recognize that. So to solve the problem, we need to create imagery that is like genuine representation of how light exists in the real world. So this is how AR should look like. It should allow us that anytime we look at the hands, we see the digital content correctly in the focus. When we focus far, the focus and blur changes. And that's what we do. There are multiple methods. We can trick the eye, try to reproduce the effect dynamically. You can have a holographic display or a light field. So like in a previous talk, we do a light field display. We create directional pixels, but unlike light field labs, shining them from panels to all possible directions, mostly to no one's eyes, we created a near-eye display which projects practically all the digital information to the eye. And this makes the light field efficiency as high as rendering a classical flat screen, flat display. There's no reason why light field should need more of anything compared to flat image, because ultimately the bottleneck in the whole visualization pipeline is our own eye. And this is how we do it. We provide the light field components in a sequence. We provide different images to slightly different viewpoints across our pupil, which together recreate the light field discretely, but as if it was a real. As far as the human vision is concerned, this is practically indistinguishable from the real light field. So of course, this allows you then to change focus at the pixels in any possible distance, close or far. And we project the image components in extremely high sequence, up to 6 kilohertz. So you can imagine the 6 kilohertz of very ugly images are bombarding your eyes, but the combined image on the retina is amazing. So this is an authentic footage which we took by a camera that is looking into one of our first prototypes, which we developed with really minimum money in a very high speed. And pay attention to the changing focus. So now the focus is on the branch and then the leaves far. This is just purely optical effect. There is no feedback loop. There is no eye tracking or camera tracking. You can also notice that you don't see any pixelation, because many of these components appear basically like many displays overlapping each other. So the pixelation smoothens. And the super high subframe rate of the light field components is an advantage on its own, because it's around 100 times faster than classical frame rate, which is very important for AR when you want to move. So in our case, there is technically possibility to display a flying bullet. And we have also a very easy way to deflect part of the image components to periphery, where we are almost colorblind and the resolution is also low. So, and this is what we have today. It's a technology demonstrator. It's not an end-user device, but otherwise it is a full-scale AR headset with an inside-out tracking, hand tracking, real-time interaction, and so on, but mainly with a light field. So again, we took a camera and put it behind the combiner, behind the glass, and this is what the camera takes. So there is no post-processing, no computer graphics involved in this footage. So again, pay attention to the focus. So everything far is blurred, and the close planets are in focus because the camera is focused on some 25 centimeters. You can read the text. I will show still photos. When you change focus, you see what you would like to see or what you are used to see in reality. And in other terms, I already said the efficiency is practically the same as for rendering flat images. The field of view is 55 degrees diagonally, and the brightness 200 nits, which can be improved relatively easily. So here is the still photo. You can see that when you focus at this 25 centimeters, you can read the panel. This is not possible with devices which have a focal plane, let's say 2 meters far. Actually, this is what you would see with other devices. But this, I'm showing basically the change of focus. This is another footage, maybe showing it more pronounced, the effect. So again, you see that when the focus is far, the hand is entirely blurred. That's normal. Also, the dragon is blurred until we focus on the hand and the dragon. And on top of it, you may notice also that the occlusion actually drastically improves because the sharp pixels nicely overlay the blurred world behind. And this is where we are heading. We are now putting practically all our resources to further scale down and customization of individual components to get the light field engine into the more socially acceptable form factor. It will be our tethered device for both computation and battery. So we are developing our own silicon drivers, modulators, and holographic combiner in-house. So in the AR development, we are quite well on track, but the market is not. So that's why we decided to do also our businesses. First is a vision care, but I won't speak about it here. And the second is a virtual reality. So we created VR headset as well. It's quite big and heavy, but again, it's a technology demonstrator so far. But again, it provides unique type of image. So again, we took a camera, put it inside, and this is what you can see through it. It is a foveated display. So the central part, which is 30 degrees field of view, is a high-resolution light field, close to 50 pixels per degree, but mainly light field. Notice the change of focus. So now the dashboard is out of focus until the camera, really manually in this case, focus on it. This is what your eye would be doing seamlessly. You would not actually notice kind of anything. You would just feel okay. Again, you can see now the change of focus from close to far. And the peripheral image is just classical flat image. So if you know Vario, so this is something like Vario on steroids with a light field inside. So again, the same effect, just more pronounced between the close camera and the car. Just imagine your eyes just feeling it absolutely naturally. Here we show the continuous focus change. That's not just like finite number of depth planes. It's practically continuous as far as we can care. Again, you see the focus went to the camera far. When we return back, the light is blurred because the focus is still far until the camera comes back. Again, I will show you some still photos. Again, authentic photo on that display. You can perfectly read pretty small fonts, but on top of it, you can again experience the normal change of focus. So that's what I wanted to show you. And as a conclusion, I would like to say that we cannot imagine the future of augmented reality without solving one of the critical problems, to provide image that is natural for our vision. And light field is one of the ways, and I think so far we proved how extremely efficient is the concept itself. We did it in 3.5 years with a very small team to now 3 types of devices, and we are continuing fast forward. Thank you very much.
Awesome. All right, questions. I know you guys have them. All right, I'm heading to the front here.
Very nice work and very nice presentation.
Thanks.
I have a question about the foveated example you gave. You mentioned Vario. My understanding is in at least some of their systems, they use physically different resolution displays. In your case, is the resolution physically the same across the whole field of view, and you're just changing the data rate, the rendering for the foveated versus the peripheral?
Now, in this VR headset, it's really just a classical, normal VR display behind. We make a black hole in the center and project the light field there.
I see.
So you can imagine normal VR for periphery, light field inside. So.
Got it.
And the resolution is different. In fact, the resolution for the periphery is more or less equivalent of the high-end VR headset from last year, I would say, like HTC Vive Pro, the same display. And you can really feel the big difference between the periphery and the center.
I see.
But, yeah.
But you're using, this is CGH, right?
Yes.
And then don't you need you're just using a traditional display as your, to display the phase information in the VR example?
No, the light field, these are combined images through a beam splitter.
I see. Okay.
So the light field is generated in the same way as for the AR.
I see.
Yeah, it's a modulated light.
Okay, great. Thank you.
All right. More questions? All right.
How's it going? Are you looking into eye tracking or anything like that to see what the user's looking at?
Yeah, this is actually a very important question. I mentioned that there is no need for eye tracking. The effect is already baked in, or the depth is baked in. But the eye tracking can, of course, help. So we have, for example, in our VR headset, eye tracker, disconnected currently. But it can improve yet again, the efficiency if we use the eye tracking. But compared to solutions which are fully dependent on eye tracking, we don't need the precision and robustness. So if it fails, actually it works still okay. I think this is quite important.
So how do you make content for it? I mean, is there like an easy tool, or are you doing like in a game engine? Could you see it in real time?
We are compatible with literally any 3D content. So currently we mostly use the Unity, but we are compatible with OpenXR. So you can imagine that we actually extract the light field information from more or less classical stereo images. It doesn't mean that we can have only 2 flat images and depth and then get the light field.
Yeah.
But thanks to moving or shaking the camera in the rendering, we recreate the viewpoints and interpolate the missing ones. And as I mentioned, the efficiency is really as high as for classical flat image plus a very small overhead. Not like 2 times, 3 times, but in percents.
But Unity is what's generating all the image or all the light field?
Well, it's our own proprietary
gotcha.
processing. So we have our proprietary format, which we need to create, then we need to decode it before projection.
I see. That's really cool.
Pastor for a second. Excuse me.
Very impressive presentation, Thomas. Thank you. Question on all these light field. I mean, one of the problems I understand, right, is it's a lot of compute power. And question on when you move to the headset architecture, is it necessary to compute all of these, you know, literally every possible light field scenario, or do you have to kind of dumb it down a little bit sufficiently to make it more of a realistic problem for computing?
Yeah, I'm glad that I can actually a little bit repeat my answer because this is very important. Before me, there was a Light Field Labs presentation, which is creating enormous amount of data. You really need a nuclear power plant to fuel it. But we are as efficient as classical image. We don't need more. Really, just this is important. The bottleneck in the visualization pipeline ultimately is the eye. There is basically a finite number of receptors. And we need to provide only what it sees. So for example, imagine that when we want to display the digital pixel here, we need to know only its coordinates and color, because then we decompose the color practically randomly to the pupil, and then it assembles again on the retina. So we need to kind of create more rays, but we don't need more information for it. We just need bigger speed to do it. So computationally, there's no issue.
Other questions?
Hi, I'm Dan Sakels, a consultant. Is your business model to license this technology? Are you going to build devices? What's the end game?
Yeah, we are a technology company, and the goal is to get our technology into products of others. And in 3 markets, as I mentioned, vision care, where it is actually pretty easy. The device can be big and expensive and doesn't need any Facebook inside. It's just very simple content. VR is very similar to classical VR. The price point is a little bit problem. So only volumes can put it down. And the AR is our moonshot, but I guess that everybody understands that we need to put forces together to make it happen.
All right, last chance. If I can ask a question, what does the future look like, say, 20 years down the road?
Yeah, well, this is also an important question because we always experienced a change of technologies or interfaces, right, from books, newspapers, and then screens and so on. And we may say, okay, then there will be AR, I would say super light, super realistic content powered by AI, simply really extending our capacity. But the question was, like, what would come after that? Well, I think that AR will be very long-standing because that's really the highest bandwidth input we have to our brain. And there is no, the next one doesn't exist. And trying to talk directly to the brain is kind of not really natural, right? We don't know how to do it. We don't understand that interface, but we understand the eyes. So this can be really long-term. Of course, the question can be where it will be glasses, how long, or the contact lenses, or implants or something like that. But I think that the glasses will be really long-standing. Very.
Awesome. That's great. Fantastic. Let's give a round of applause. That's fantastic. Thank you so much, Tomas.